Hello, Professor. My name is Simon Kilari. Now I'm going to explain how I solved the closed pair of points problem using brute force and divide and conquer algorithms. In this problem, we are given n points in 2D plane, each with coordinates x of y. Our goal is to find which 2 points are closest to each other in terms of LCM distance and to return the instance of 2 points, not just the distance. This problem is how different algorithm strategies have come to the task. Next slide. When it comes to the brute force pseudocode, here we simply check the distance between every pair of points and keep track the minimum distance we see and return that. Because we use it to 2 nested loops, over the points, the running time grows like n square, so it becomes slow as it gets larger. And when it comes to the divide and conquer pseudocode, we first sort the points by x coordinate and recursively solve the problem on the left and right half, and we take the similar of these distances and then look at the narrow strip around the middle and checking only the points that are closest to each other. This reduces the work, gives a running time of theta log n log n, which scales much better. When compared to both algorithms, brute force runs on theta of n square and divide and conquer follows theta of n log n, which scales better for larger inputs. For small n, both algorithms are comparable, differences grows n increases, and predictor runtimes using C1 and C2 closely match the empirical measurements. Now I'm going to show my code implementation and how it works. To the VS Code. Here, I used Java for implementation. For the implementation, I use Java to run both algorithms. First, I generate n random 2D points using a point class x and y coordinates here. Then I move to the distance function that computes LCM distance between any 2 points. The brute force method loops overall possible pair of points using 2 nested loops, keeps track of the smallest distance seen so far, and returns that are closest as per distance. Because it checks every pair in theoretical runtime of n square, and it computes theoretical n square for each input size. When it comes to the divide and conquer, I first sort the points by their x coordinates and then recursively split them into left and right halves to the closed deal function. After solving each half, it builds a narrow strip around the midline and only compares near the points in that strips, sorted by the x coordinates. And it has a theoretical RT of n into log n. For both algorithms, I took 10,000 values of the starting inputs to 100K, run each size 10 times, measure the average runtime in milliseconds, and store everything into two CSV files here. And I use Python here to load the CSV files and display using the MATLAB by using empirical brute force and divide and conquer for each algorithm. When it comes to the output, the graphs clearly show the brute force much faster than divide and conquer scales, confirming theoretical theta of n square versus n log n behavior here. And for the results, I have seen the C1 with a maximum ratio of 0.04856, and for C2 divide and conquer, the maximum ratio is 0.009992736. And when it comes to the conclusion, the project shows like brute force is simple but becomes impractical for larger data sets, and the divide and conquer algorithm efficiently reduces and compares scales to larger n, and empirical results aligns between the theoretical complexities, that is theta of n square plus theta of n log n. Thank you, Professor.